Is the singleton of the empty set the same as the empty set? After all, both of them feel like they're empty, right? The empty set, you can imagine, is like a box that when you open it, there's nothing in there. And singleton of the empty set is like a box that when you open it, there's another box, and when you open that, there's nothing in there. So are those the same? They seem to have the same elements, right? I claim no, they are not the same, and they do not have the same elements. So that's what we will prove in this video. So claim, or we could say theorem, this is not equal to this. So how am I going to prove a non-equality? Well, one approach is to do a proof by contradiction. So suppose for the sake of contradiction that these are equal. Then, if they are equal, can we get a contradiction? So in order to get a contradiction from this, we need to think about what power knowing this fact gives us. What does this enable us to do? If we know that two things are equal, then the main thing that we can do is what you see here in what we're calling equality used, axiom 2 or theorem 4. If two things are equal, then anything you say about one of them, anything you can say about one of them is equivalent to if you said the same thing about the other one. So if these are to be equal, which I'm assuming for the sake of contradiction that they are, anything I say about this one holds equally well about this one. That could be a way to try to get a contradiction from here. Can I find something that can be said about this, or about this, but which would be false if I said it about the other one? That is a way of proving that two things are not equal. Find something that is true of one of them, but not true of the other one. Then axiom 2 will lead to a contradiction, as you'll see. So if you want, you can pause the video now and think about what property one of these two has that the other one doesn't. What property do you think I'm going to focus on? Okay, and here's the answer, at least what I'm recommending. Maybe you can find a different solution, but the main property of the empty set that we know is that it is empty. And one of the main things about a singleton that one can prove easily is that if you take singleton x, then x is in it. It's an element. So it is not empty. It has something in it, at least, which is the one thing that you've written between the curly braces. So I guess there were two possible answers. You could focus on the property of emptiness. This is empty, and if they're equal, then therefore this is empty. But you can prove this is not empty because it has this one thing inside it. So that's one way to go. Or another way to go is focus on this to start with instead. This has an element, specifically this one. Therefore, if they're equal, then this has an element, but that contradicts the emptiness of this. It's pretty much the same thing, those two lines of argument. Those are pretty much the same thing. So first, my goal becomes, so I'm going to take the second approach. First argue that this is an element of this. That's my first approach. So how would you prove, in general, how would you prove that x is an element of singleton x? Well, remember the definition of singleton. This singleton x is the set of things that equal x, right? So to prove that x is an element of that, I'd have to prove that x equals x. So that's where this idea is coming from. Since this equals itself, that's axiom 1. We have, using axiom 5, that this is in the set of things that equal the empty set. The empty set is in the set of things that are the empty set, because the empty set is the empty set. Okay, then by axiom 2, since this thing equals this thing, and it shows up here in this proposition that I know is true now, I can replace this by something equal to it. So I now have this. And this is not a contradiction. I mean, technically, what we refer to as a contradiction is a proposition, something of the form phi and not phi. So you need some way of writing this and not this. But here's the contradiction. So the reason this feels wrong is that the empty set is empty. So you should never have something be in it, right? And if I go back here, empty set is empty. This theorem, x is not in there. X is free here, so I can put anything for x. Replace x by any term. Any given thing is going to be not in the empty set. So in particular, applying theorem 12 to the case where I'm replacing x by the empty set, by theorem 12, the empty set is not in the empty set, because nothing is in the empty set. So this is a contradiction. Specifically, what is a contradiction is this fact, that I have this and this, something and not itself. Okay, so even though both of these things feel like they are empty, they are different things. This one is truly empty, it has no elements, but this one has an element. So they cannot be the same thing. So when you're imagining, boxes within boxes, include in your imagining of what's going on, include not only what things are inside the boxes, include not only your imagination for what non-box things are in the boxes, but also include in your imaginings what is the box containment structure. Like, a box in a box really is different than just a box, even when everything is empty and there's nothing in the deepest box. Okay, and a natural next question is, okay, what about I package those two in boxes? Then I cannot pull this argument here using theorem 12 to show that these are different. So are they the same? It turns out no, they are different. They are definitely different. One is a box containing an empty box, the other one is a box containing a non-empty box. So if you want to, you can think about how you might formally prove that they are different.